Good afternoon, everyone. It's a pleasure to be your host today. My name is Amal Coad. I spent 6 years as PhD and further as postdoc at EPFL in Switzerland, making research in the field of self-healing composites. And I now run a startup company with a great technology following those years of research. Thanks for joining us for the third edition of the Composites Challenge. The Composites Challenge is an international competition with the aim of creating a link between researchers and industrials. How did it start? Inspired by some lightning talks in the field, we realized that this was a need for our composites industry as well to push forward this link. So here is how things are going to work. To discover the next generation of composite leaders, we selected 10 PhDs from around the world to present their research. But we asked them to do it in less than 5 minutes and to use only one slide. Each presentation will be followed by a 2-minute Q&A with the jury. So I'm pleased to introduce our fantastic jury today, composed of academic and industrial experts in the field of composites. We have Christophe Benetruy, professor at École Centrale de Nantes, Christian-André Keun, former president of Sampi Europe and CEO at Composites, Lucien Fior, Asia Pacific Business Development Director at Excel, Véronique Michaud, professor and head of the Laboratory for Processing of Advanced Composites at EPFL, and Jean-Marc Sénéco, Global Head of R&D at Porsche Industries. They will have the tough task to evaluate the 10 finalists and select one winner. Hello to all of the jury of today.
Hello.
Hello, thanks all, and we see you in a minute for all the questions, and enjoy the talks. Great. The winner of today will get a VIP ticket to the next year's JEC World Edition from the 8th to 10th of March 2022, and a snazzy dinner for two at Restaurant Jules Verne at the heart of the Eiffel Tower, and we are confident about next year's situation. So, everyone, are you ready? We can welcome the first contestant of today. So please welcome Simone Bancora from École Centrale de Nantes. Simone is originally from Italy and followed a double degree program between Milan and Nantes. He's working on processing of composites, crucial for efficient manufacturing. The title of his talk today is From Compaction Pressure to 3D Geometry, a scalable method for preform characterization. Simone, are you ready?
Yes, I am.
Great. So 3, 2, 1, and go.
Thank you. Allow me to open my presentation today in a fitting way by asking you, what is so challenging about composite materials? Well, for starters, they're not even materials until you actually make a part with them. Let's focus our attention on liquid composite molding processes. It is only when layers of textiles are placed inside a mold and compacted that the complex network of yarns and channels really takes shape. But here lies the challenge. Once the mold is closed, it becomes difficult to track the position of layers, yarns, and eventual deviations from the layup. This is why it's hard to predict properties of a dry preform and run filling simulations that might help to predict defects. It is also why, in my experience, working together with more than one company, I found that rather than trying to simulate something so unpredictable, we sometimes rely on trial and error and deal with defects as they come. So can we do better? What if we could actually take a peek inside the closed mold, grasp the essential features of our dry preform, and characterize our material by running some numerical simulations based on real data? Well, today I present you a new methodology which aims to do just that. I'll take you on a little journey, step by step, as represented on my slide, from the moment we place our material inside the preforming mold up to the moment we get some characterization by simulation. Our story begins with the flexible pressure-sensitive film. I have a sample right here with me. When layers are placed inside a preforming mold, We place this film on top of them, and it will capture the pressure field felt by the preform during the compaction. Now, the interaction between layers originates some patterns on the pressure field, as you can see at the center of my slide. I like to see them as a signature, if you want, of the preform. And we can analyze these patterns by combining principles from Moiré theory with tools from image spectral analysis to extract and interpret the orientation and the spatial distribution of toes for every layer in our preform. Now, with this kind of geometrical information, we can go ahead and build a digital twin of our material, a three-dimensional representation that carries over the same mesoscale features of the original. And one key aspect of this technique is scalability. This pressure film can be placed over a large surface, meaning that we can study and reconstruct a full-scale part if we want to. But this kind of three-dimensional representation is really too detailed to run a large domain computation on it. This is why we need to go one step further. Now, we strip our digital material of non-essential geometrical information, and we extract the skeleton representation of the same, with branches describing both yarns and channels. Now, this is the convenient, affordable representation of our preform. On this dual-scale skeleton, we can run numerical simulations and extract some properties characterization. And now, finally, we have reached the destination of our journey, characterization by simulation, which is based on the real data from the material we have inside the preforming mold that can be useful to predict defects over a large domain. I would like to conclude by saying that I believe in the potential of digital tools as a support to the physical manufacturing processes. Now, this has been going on for years, and this methodology right here is no difference in that sense. And it could be easily integrated in currently existing LCM manufacturing workflow without the need for additional steps. I believe in the potential of this technique for digital characterization, which has reached today a good level of development, and I hope I'll be able to bring it to the industry one day. Let me just thank my advisors, Professors Binetri, Advani and Comas, as well as all the people at the École Centrale for the support through this journey. Thank you.
Thank you very much, Simone. Do we have some questions from the jury?
Please.
Very nice presentation. Thanks a lot. Did I understand right? If you've got several layers of textiles, so between every layer, there has to be one pressure-sensitive film, I would say, to detect the orientation of the fibers? This is the first question. Second question, if, for instance, you have an RTM process, you know that by injection of resin, sometimes the fibers will deviate, show some deviation. You can also, does your pressure film resist RTM processes?
Excellent questions. Thank you very much. I will answer right away. So for the first question, the way this technique works actually is you just need to place one layer of this pressure sensitive film either below your preform or on top of it, just one layer. Mm-hmm. And the interaction of all the layers on top, so you don't need to put it in between the layers, actually exhibits some patterns because there is some interference in the thickness of the different layers, which behaves in a similar way to the interference of gratings in Moiré theory. So just one film is enough. Mm-hmm. And of course, you're going to have a limitation in number of layers, but I've been able to push it up to 9 layers without any difficulty. So yeah, this is the way it's meant to be used. Regarding the second question, this technique has been only used to characterize a dry preform. Okay, so either in your preforming mold, in your preforming phase, you can place this film, and then when you retrieve your preform, you have the information to reconstruct its information and its architecture. But it has not been tested in the context of my thesis. But there are researchers using this kind of pressure film in environments with fluids inside, meaning that it can be sealed to be isolated from the fluid. Now, I cannot tell you, I cannot vouch for it, I cannot tell you if this would work. But one thing which is very interesting in this technique is that the interpretation of these pressure patterns gives you orientation, but also gives you, very importantly, the frequency, the spatial frequency, which relates to the period, the spatial periods of yarns. So if you had some wash up of fibers or yarns which are getting further apart, let's say, if we could capture the right pressure information, the pressure could give you that information. But the unknown is, can it work under fluid environment? That has to be tested.
Thank you.
Thanks a lot, Simone. We will get a quick question from Véronique Michaud as well. And please, Simone, answer in a concise way.
Sorry. Yeah, I just had a question concerning the droppability of your film, because you show a very complex shape, like a hemisphere in your slide.
Yeah.
How would you conform this sheet of film onto a hemispheric mold, for example?
Yes, it's a good question. So for this kind of pressure film cannot be used on double curved shapes. There is no mapping from this material to a double curved shape without distortion, so it cannot work. With single curvature shapes, it's okay. As long as you can apply, that depends on the specifics of the mold and the quality of your mold, a pressure which is normal. You do not need to apply shear forces to this material, because if you apply some shear force on it, the microcapsules on it, they break in a non-controlled way, so you cannot have the right information. As long as you apply a normal force with curves, it works. It's single curves.
Yeah. Thank you.
Thank you very much again, Simone. And now please welcome our second candidate, Carl Bouton from KTH University in Sweden. Carl is originally from France, and he joined Sweden to work on a hot topic with many partners, using composites as batteries. The title of his talk today is Structural Power Composites from Massless Energy Storage. Carl, are you ready?
I'm ready. Thank you, Amel, and thank you for giving me the opportunity to present my work today. I would have liked to fly to Paris from Stockholm, and I would have been even happier if I could have fly on board an electric plane. The problem is that nowadays you can design an electric plane that carries 120 persons on that kind of distance. So you need to find new ways, new design, new materials, new tricks. And because one of the main reasons is the weight of the battery pack, the idea would be to store some electricity, some energy in the frame of the aircraft. That way, you don't need to store much energy in the battery pack. So you could reduce the size of the battery pack and save weight. And there's a class of material that is meant to serve this purpose, and they're known as structural batteries or structural power composites. As multifunctional materials, there's structural batteries are mechanically robust, strong, and so they can serve as structural components. But they can also store energy, electricity, or electrochemical energy, if you prefer. They also laminate composite materials, so they include several layers. They include electrodes, carbon fiber-based electrodes, an anode that is just bare carbon fibers, and a cathode where the carbon fibers support lithium oxide particles. You may find in between some glass fabric that prevents contact between the electrodes. And there is a fourth secret ingredient into that, and that's a special kind of thermoset resin, SBE, for structural battery electrolyte. Like an epoxy or a vinyl ester resin, this resin is can transfer load between the fibers and the different plies, but it's also ionically conductive, so it can conduct lithium ions. Then this resin is infused through the battery stack by a vacuum-assisted resin transfer molding process and cured at 90 degrees to finally give something that looks like the pictures you have at the center of the slide. And honestly, you would not tell the difference between a structural battery and a conventional piece of composite, from the outside at least. Because if you look inside, there are quite a lot of things happening during charge and discharge. And you have to remind that carbon fibers are not only reinforcement material, but if you set some electrical potential to it, the carbon fibers have the ability to host lithium ions. And then from an electrochemist point of view, it's a very good electron material that can host lithium ions during the charge, or release lithium ions during discharge or when you draw power from it. So that way, and you will find that on the graph, we could achieve a structural battery with an energy density of 24 watt-hour per kilograms and an elastic modulus of 25 gigapascal. By improving our process, our manufacturing process, our method, we could triple or quadruple these values. But neither the elastic modulus or the energy density of the structural battery will ever equal or even exceed the elastic modulus of a conventional carbon composite or the energy density of a conventional battery pack, like the one you would find in a Tesla car. So from this figure, it's not obvious whether or not the structural battery would allow mass saving, whether or not it can bring benefits. But think of a drone or the chassis of an electric car, initially made of carbon composites. If you shift to structural battery, your structure may be slightly heavier because the structural battery is less stiff, so you would need more material to bear the same loads. But now the structure have some extra energy storage capabilities, so you can reduce the size of the battery pack and move a part of the energy in the structure. That way, there is a threshold for which the mass that you save on the battery pack exceeds the additional structural weight. And that's where the magic is, where with multifunctional materials and structural batteries, their strengths lie in the fact that you combine two functions within one single piece of material. And that maybe in the future will allow a Stockholm-Paris electric flight. Thank you.
Thank you very much, Carl, and thank you very much for the exact and precise timing. Congratulations. Do we have a question from the jury?
Yeah.
Yes, Jean-Marc, go ahead.
Hello, everybody. Thank you for your very clear presentation. Interesting, and I like the storage energy, and very interesting to combine the structural part on the battery. It's a dream I have as well. I have two questions, very simple question for today. One question is on the battery. Do you measure the number of charge and discharge you are able to apply in your concept today?
Yes. If you're talking about the discharge rate, I mean, these batteries are mostly made to work with a discharge rate of 10 hours. But with by modifying the battery chemistry, you could work on a shorter discharge rate, like an hour, and then this battery can serve for hundreds, thousands of discharge rates. So yeah, it's a matter of chemistry and some work to be done on the chemistry side. Yes.
Very quickly, second question, if I may, is the properties. You mentioned you use a ionic ion-conductive resin, if I understood well. What is the properties of this resin? Is it brittle or ductile resin?
No, can you repeat, please?
Is it a fragile resin? I would say it's a ductile resin or brittle resin.
It's not brittle, or it's more like a ductile resin. I mean, it is based on bisphenol A. So basically, the kind of chemical components that is the base of an epoxy resin. So it's very similar in terms of properties. Yeah.
Okay. I have more questions, but not today, sorry.
Thank you very much for those questions. Thank you, Carl, for the answers. A really quick question from Christophe Bintouilly as well.
Yes, thank you very much for your presentation. Just a quick question. You presented elastic properties for the mechanical properties. Did you investigate like fatigue properties or like?
No.
Just to see. Okay.
No, actually, and I could just say a little bit on that. We didn't investigated the fatigue properties, but that is something to be investigated because the lithium ions intercalation process will lead the carbon fibers to be weaker and weaker over time. So that's something to look at for sure. But we didn't do it yet.
Okay. Thanks.
Thank you.
Great. Thank you very much. We can now move to candidate number 3. Please join me to welcome Callum Brandfoot from the University of Bristol in the UK. Callum is native from the UK, where he passed his degree in chemistry. He's working on new types of resin to improve the life cycle of composites. And the title of his talk today is Reversible Cross-Linked Polymers and the Future of Composites. Callum, are you ready?
Yes, I am. Thank you, Emil.
Great. 3, 2, 1, and go.
Hi, everyone. So I'm Callum, and in this short talk, I'm going to bring together 2 concepts for you. One, CANs, which I'll explain shortly, and the other, 2, sustainable composites. So if I could draw your attention to start off with to the top middle of the slide, you can see a simple composite part, a skin stiffener there. And let's say that's carbon fiber epoxy, for example. Now, if we imagine the life cycle of this composite, then there are several points at which we might generate waste in that. So 1, in manufacture, due to defects and offcuts, there's likely to be some scrap. 2, in service, badly damaged parts as well might be prematurely scrapped and lead to waste that way. And 3, at end of life, because at present there aren't currently any commercially viable recycling methods for conventional composites. They are either landfilled or incinerated. So the net result of this is that fiber-reinforced polymers are generally either incinerated or landfilled. So together, composites aren't as sustainable as we would like them to be. So one way in which we might be able to make more sustainable composites in the future is to replace our polymer with a novel functional polymer, such as CANs. What CANs are, and they stand for covalent adaptable networks, is a cross between the 2 main types of polymer, so thermosets and thermoplastics, but the key is that they have reversible cross-links, so they can be partially depolymerized on command. Now, if you look at the top right of the slide, maybe you have to look at move the image there, you might be able to see these molecular zoomed-in view of this CAN concept, and this is how CANs might work when applied to self-healing. So the white circles follow the polymer backbones, and the blue circles the cross-links that hold them together. Now, if we imagine this in a composite that is damaged, perhaps by an impact, there could be some micro-cracking, say. We want to repair these cracks, and then maybe we apply a stimulus such as heat or ultraviolet light to the surrounding area, and this may decross-link those blue circles, pull them apart to those red ones, and that gives the polymer backbones the mobility to flow over each other, fill cracks, and repair damage. Now, if we remove the stimulus, our heat or our light, then the crosslinks can reform, and importantly, we can restore the mechanical performance we had to begin with. So if we look at the bottom right of the slide, we can see how the thermal behavior of one of the CANs, thermally activated ones that I made during my PhD. So looking at the DMA, we can see the black curve. At low temperatures, we're dealing with a 2 to 3 gigapascal modulus, so not unlike a conventional epoxy. But as this one is heated up past 100 degrees or so, it goes through a glass transition and straight into a melt. So what you end up with is a liquid with no modulus at all. Now in the rheology below it, we can see again the black curve sharply drops off as temperature rises, and this follows the decross-linking process. Then as the temperature is reduced, it recross-links again, and importantly, we can see that this process is repeatable again and again and again. Now, if we have a polymer like this, we put it into our composite as our matrix, there are several ways we can apply this to improve the composite life cycle and make it more sustainable. compared to normal composites. So one, in manufacture, we can repurpose, reshape scrap because we are partially uncuring the polymer every time we mold it. So if there are defects as well, we can just try and mold our composite again. At two, in service, if there's damage, we can repair our part in a self-healing strategy like the one in the cartoon figure to the top right of the slide already discussed. And in the photos, we can see at the bottom of the slide here some 3-point bend specimens where I've demonstrated this. So we can get really quite good healing efficiencies with composite and polymer made of these cans, but I've deliberately left in this low one here with this 28% healing efficiency as a little reminder what we cannot do is repair fiber damage. So that's why that is quite low there. And maybe most crucially of all, at end of life, we can develop new recycling methods that work with cans, such as this solvent-assisted one that I've shown in these photos here. So we put our composite into a solvent, it swells up, and then we can easily separate the fibers and polymer, dry them out, and reprocess them into new composite that has good strength and therefore good value and can be used going forward. So 70% strength there. And finally, 3B at the far bottom of the slide, you can also improve end of life by using these polymers as reversible adhesives. So with that, hopefully I've convinced you that cans are quite interesting new materials, and hopefully we'll be working together to make more sustainable composites from them in the future. Thank you.
Thank you very much, Callum, for this really nice talk. Do we have some questions from the jury? Yes, we have.
Hello. Yes, hello, Callum. Thank you for this really nice presentation. I have a question concerning the processing of those composites, because the viscosity seems to be very high when you melt it from what you showed. So can this be processed by a liquid composite molding, or do you need to use like press forming techniques?
You need to use press forming with the with the polymers, the cans that I've developed at the moment, the ones I showed you. They treat them as powders and then compression mold them essentially, high temperature and high pressure. But it works quite nicely.
Okay, thank you.
You're welcome.
Great, thank you very much, Callum, again, and congratulations. And now, please welcome the next candidate, Kelly Chang from University of Illinois at Urbana-Champaign in the US. Kelly is passionate about sailing, which gave her the wish to study multifunctional composites through a PhD. The title of her talk today is Autonomous Healing and Indication of Cracks in Fiber Reinforced Composites. Kelly, are you ready?
Yeah, let's do it.
Okay, great. So 3, 2, 1, and go.
Hi, everybody. I'm Kelly Chang, and yes, I am a PhD student at the University of Illinois, but I'm also, as Mael mentioned, a competitive sailboat racer. And in 2015, a 20-foot carbon fiber mast broke at its base, fell squarely on my head, and before I knew it, I was in the hospital with a concussion. Now, this mast was only 2 years old, but it had been used so many times in those 2 years that it snapped under completely normal use. This is called fatigue-based failure, which manifests in fiber-reinforced composites as transverse microcracking. These microcracks accumulate over time, causing composites to fail at stresses considerably lower than their static strengths, and is the main reason why structural composites have a limited lifespan. Now, the global composites industry is an estimated $89 billion and growing, and so of course there's an increasing demand for addressing this limitation. And so we thought, what if that mass were more like a broken bone? Our bodies have this amazing innate ability to sense pain and then heal what hurts. What if that mass could heal itself too? What if it could even warn me when it was hurt? And what if we dreamt even bigger? What if the Boeing 787 or the satellites orbiting the Earth could do this too? If we could easily heal and indicate and identify microdamage before it became dangerous, not only could we avoid masks to the head, but we could drastically increase the lifespan of our boats, planes, cars, and satellites, avoid lengthy and highly manual out-of-service repairs, and prevent other potentially catastrophic failures from occurring. My research group took this bio-inspiration and developed an elegant pathway to composites that both self-heal and self-indicate microdamage. This novel idea involves embedding tiny microcapsules containing both a healing agent and a special dye in our composites. And so to do this, we first mix a liquid solvent with a special dye that glows or fluoresces under UV light. And this dye is extra special in that suspending it in a solvent actually suppresses its ability to fluoresce or glow until that solvent is removed. We can then store this liquid mixture in tiny microcapsules, deposit the capsules on carbon fibers, and then embed these fibers in a thermoplastic toughened epoxy matrix. And so from my slide, you can see that self-healing and damage indication begin immediately upon damage in this material system. As cracks propagate, the embedded capsules will burst and release their liquid cores. Then the released solvent will dissolve local thermoplastic, distribute it into the damaged areas, and finally evaporate to leave solid thermoplastic in place of the original damage. And meanwhile, the solvent is also transporting our special dye into the damaged areas, which will evaporate and finally allow the dye to activate in those healed areas. And this will make it significantly easier to see microdamage. So far, we've demonstrated that the solvent-filled microcapsules can actually survive the conventional composite manufacturing techniques we use today. And at the macro scale, we've demonstrated a 420% fatigue life extension using this strategy. That would mean adding another 6 years of life to that mast that I had an encounter with, and another 90 years to the Boeing 787. And so what's next to learn is what self-healing in the 787 would look like at the micro scale, and if we can also introduce simultaneous damage indication. And this is my thesis work. So to test our material's dual functionality at the micro scale, I make small composite samples about half the size of a matchstick and pull on them under a microscope until they crack, like in my top left image. I then allow them to heal and repeat the same test. And to evaluate healing, I can use a computational technique called digital image correlation to track the motion of the carbon fibers and finally calculate the deformations across the entire surface of each of my samples. And the second test I conduct is to shine UV light on my cracked samples to confirm that our special dye has activated in the damaged areas. And so by correlating local fluorescence with local recovery, I'll be able to verify simultaneous self-healing and damage indication. Quantitative tests are still in progress, but preliminary results confirm that cracks both glow and contain thermoplastic after rest. Moreover, our composites have demonstrated self-healing with just 1% of capsules by volume, which means they won't deteriorate the structural performance of our composites in their virgin states. All told, our bio-inspired self-healing and self-indicating composites are poised to reduce manufacturing and maintenance overhead by extending the safe and usable lifespan of these materials. I'm really excited about this technology, and I thank you for letting me share it with you.
Thank you very much, Kelly, for this really nice talk. Do we have some questions from the jury? Yes, questions are coming. Christian, you can go ahead.
Sorry. Only one question. You have got unique thermoplastic modified epoxies for thermostats for this healing process. How much is the content of this thermoplastic? Because this is very necessary to reach every point which could be a crack.
Yes. So right now we're using a 20 weight percent formulation, and that's enough.
Thanks.
Mm-hmm.
Christophe?
Yeah, very quick question. Thank you for your talk. About the dye you introduced in the material, is it visible from outside the composite materials, or you need a special device to see it?
It's so it's UV activated, so you need for UV light to penetrate the material in order to activate the fluorescence, and so by that nature, it's visible on the surface only.
On the surface only. Yeah. Thanks.
Great, thanks a lot. Let's take the third question. Quick one.
Yes, hello. Thank you for your great presentation, and I know the self-cleaning as well. I like this story. One question: do you know the speed of the self-cleaning you have in your composite?
So far we've not been able to characterize it at the small scale that I'm looking at specifically, but my group has demonstrated self-healing under just 2 days, which is great for, which is really promising for this technology.
Okay, thank you.
Really great. Thanks a lot. And we
Thanks.
look forward to seeing the next step of this research.
Thank you.
We are already reaching candidate number 5. Please welcome Gerard Clancy from the University of Limerick in Ireland. Native from Ireland, he has already work experience in the energy sector. He went back to academia for pursuing his PhD that is dealing with improving fiber placement methods. His research led already to a patent, and the title of his talk is Spreading of Carbon Fiber Thermoplastic Prepreg Tapes. So Gerard, are you ready?
I am indeed.
Really great. So 3, 2, 1, and go.
Efficiency is vital when it comes to composite structures. We want components to be stronger, yet lighter, and also you want to make them quicker for cheaper. When it comes to complex components such as aircraft noses or engine casings, current composite manufacturing methods struggle to produce these efficiently. The reason they struggle is such components are doubly curved. To explain this better, everybody here has probably had to gift wrap a present at some stage. When I give a present, I like to give books, not for certain obvious reasons, but because they're easy to gift wrap. They're a simple rectangular shape, there's little use of sticky tape, and there's efficient use of wrapping paper. Now, has anyone ever had to gift wrap a football? It's a completely different task. It's quite complicated. There's a lot of sticky tape, there's excessive use of wrapping paper, there's overlaps, there's wrinkles. It's just an inefficient use of material. Composite manufacturing methods have the same issue. They use rolls of fabric or tapes which have constant width to try and cover a doubly curved surface. To explain this better, so they either have to overlap the material, which adds unnecessary weight, or they have to cut the material to a certain shape which induces fiber cuts and therefore reduces strength. What would be a more efficient method would be having the ability to vary the width of the material as it's laid into position without fiber cuts. To explain this better, take a beach ball and see how it has these individual sections that vary in width. They're wider in the center or at the equator, and then they're narrower at the tip. I have designed a manufacturing method which has the ability to vary the width or spread carbon fiber thermoplastic prepreg tapes. A small device will be incorporated into an automated tape placement machine, which you can see in image 4. And how this works is that the automated tape placement machine has a carbon fiber prepreg tape is fed under a roller, and the incoming tape and substrate is melted with a laser beam, and the two are compacted together. The small device that I've designed will be incorporated into the automated tape placement head and would have the ability to vary the width of the carbon fiber prepreg tapes before they're consolidated into position. The most important thing is that there will be no fiber cuts in this, and we'll be able to achieve these variable width sections that we see in the beach ball. The device that I've designed is quite small. It can fit in the palm of my hand. We can see a small image of it here in picture 6. And how it works is that there is a heated platen with 2 compaction shoes. The carbon fiber thermoplastic prepreg tape is fed through the small device. The heated platen melts the thermoplastic resin, and then the compaction shoe applies a downward force on the melted resin and fibers. This squeezes the tape and then results in an increase in width. We completed many different spreading trials, trying different processing parameters such as different temperatures, pressures, and pull-through rates. There was a lot of failed attempts, but we eventually achieved successful results where we were able to get an increase of 62% in width. Once we were happy with the spreading technique, we needed to investigate, does this spreading negatively affect the quality of the tape? We actually discovered that the spreading appears to improve the quality of the tape. As you can see in image 8, I have 2 optical micrographs, one of an original as received unspread tape and one of a spread tape with 30% increase in width. As you can see, there appears to be an improvement in fiber dispersion with less resin-rich areas. Also, we measured that there was a reduction in voids in the spread tape in comparison to the original tape. We also completed crystallinity tests, and we found that the spread tapes had an increase in crystallinity, which is beneficial as increased crystallinity results in improved strength and improved fatigue performance. Further tests are required to see, does this spreading negatively affect the quality of the tapes at laminate level? We also have to do a lot of work in trying to incorporate one of these spreading devices into an automated tape placement machine. But to conclude, this is a simple manufacturing method which has the ability to reduce the weight of aircrafts, to boost efficiency, to reduce emissions and reduce waste from the production process, all with just a small additional cost to the manufacturing method. Thank you.
Thank you very much for your really nice talk. Do we have some questions from the jury? Yes, Christophe Benetruy, go ahead.
Yes, thank you very much for your talk. I have a quick question about having this device introduced in the head of the fiber placement machine. What is the maximum velocity you can reach? Because if I understood clearly, you have to squeeze the material before laying down. So I think it takes some time. So I'm
correct.
sorry.
Yes. So the speed would not be the same as you can achieve without this device. We're talking at 3 meters a minute, because once you go above that, our current method induces, there's friction on the surface and it makes it difficult to control the heat then. So 3 meters a minute.
Yeah. Thanks.
Thank you very much. Let's go for the second question.
Hello, do you hear me?
Yes.
Yes.
Yeah. Okay, thank you. Just a question regarding the properties that you may have between the spread and unspread materials. What at the end you have been able to achieve in terms of, are you keeping the same performances, or do you have any reduction due to the fiber distortion?
Yes, so in terms of the volume, we're keeping the same volume within the tape. I will admit it is currently early stages. Let's say the consistency of the width is probably not as good as the consistency of an as received tape, but we are working on this. It is close, but it's not perfect at the moment.
Great. Thank you very much for your talk, for the questions. We are already at the middle of this session. I hope that the jury and all the contestants will be good. An important note, as of now, you can see the technical posters of the 10 finalists in the Education Hub on the Digital Trade Show of JEC Connect 2021. Don't hesitate to pass by if you want to get more information on each research. Okay, so now let's go for our 5 next speakers. Please join me to welcome Christopher Hunt from the University of Bristol in the UK.
Thank you, Emma.
Christopher is the winner of the SEMPI Europe edition of last year. He's working on novel lightweight composite structures. And the title of his talk today is Raptor Composite Truss Structures. Christopher, are you ready?
Yep, ready.
Great. So 3, 2, 1, and go.
I want you to take a moment to think about why you are here today. Perhaps you're searching for a new business partnership or a new job, or maybe you're just really interested in composites. But I want to suggest a more fundamental reason as to why you're here, and as to why we're all here, and to why this event even exists. And that reason is because we want to lose weight. Now, I don't mean getting back into shape after several months in lockdown. I mean losing structural weight. The desire to reduce weight in engineering stems from the fact that in so many applications, weight is coupled with fuel burn, which is coupled with environmental damage and operating costs. But how do we actually lose weight? Well, as a structural designer, you've really only got 2 options. You can change the geometry of your structure, or you can change the material that you use within that structure. On the geometry side, one choice that has been popular throughout history has been the truss structure, a classic example of which is this bridge. Now, trusses are great because they allow you to make really strong and stiff structures while using a minimal amount of material. To explain how they do this, I want you to imagine you're holding a pencil. If you pull that pencil along its length, you probably won't be able to break it. If, however, you bend it, then it breaks very easily. And this is because bending moments are really hard for structures to withstand. And what a truss does is it creates a structural system in which all of the members are primarily loaded along their length. Now, on the material side, one option of increasing popularity are composites. We obviously all know that composites have fantastic specific strengths and stiffnesses, but really the applications in which these materials excel are those where there is a dominant loading direction and where that direction is known, because in these applications we can take advantage of the anisotropic material properties by aligning the fibers with the loading direction. The point I'm trying to raise here is that if you have a geometry where all of your members are loaded along their length, then it would make sense to make these members from composite materials, because you could easily align the fibers with the loading direction. So if composite trusses are so great, then why aren't they used everywhere? Well, conventional trusses like this bridge require joining of many, many parts. When you consider the notorious difficulties associated with joining composite parts, manufacturing a whole truss structure then becomes a bit less attractive. So this is where our technology comes in, the Raptor truss, which stands for Rapto Reinforced Truss. This technology uses a novel winding process, which allows us to make composite trusses without the need to assemble a huge number of parts. For this process, which is depicted in the lower left of the slide, we take 3 rigid carbon fiber tubes and we hold them on a mandrel. That mandrel is then rotated and a wetted carbon toe is wound over the mandrel. The structure is then left to cure, the mandrel is removed, and we are left with the truss configuration seen here, or in the center of the slide. The resulting trusses are extremely efficient. Experimental tests have shown the trusses can carry 3 times the load and have 10 times the stiffness of an equivalent mass unidirectional carbon tube. The trusses are so efficient that their use within their original application, the game-era human-powered helicopter, resulted in a 40% reduction in airframe mass. This led to the break-in of a number of world records for human-powered helicopter flight. Now, while this helicopter is incredibly impressive from an engineering standpoint, in real-world terms, it isn't that useful. So that's where my work comes in. My aim is to develop this truss technology to the point where it can be used in useful real-life applications. To do this, I'm focusing on two main areas of work: manufacturing and analysis. On the manufacturing side, I'm trying to develop and improve understanding of the winding process. Having completed the design and build of an automated truss winding machine, I am now able to produce these trusses quickly, repeatably, and at a surprisingly low cost. As well as being able to make these structures, we also want to be able to predict their structural behavior. That's why I've been developing analytical tools which are now capable of accurately predicting truss stiffness and are also capable of making reasonable approximations to truss failure loads. Upon completion of this work, I hope this technology, which is the perfect combination of geometry and material, will be ready for implementation in real-world applications. And hopefully this will partially satisfy our constant desire to lose weight.
Thank you very much, Chris, for this really nice talk, and we look forward to seeing the next step with those structures. Do we have some questions from the jury? Yes, we have one.
Yeah, thank you, Chris, for your nice talk. A quick question on my side. I would like to know if for this type of structure, what about, for example, the complex loading conditions? So, for example, if you combine a bit of bending with torsion, so have you already studied that with your new technology?
No, so I haven't done any experimental combined loading. We have looked at it in the analysis. Most of the loading scenarios we've looked at has been bending, but we're also starting to look at compression now. So those are the two main ones that we think will be most useful for, so bending and compression.
Okay, thanks.
Great, thank you very much. If we have a second question.
One small question. Thank you very much for a very nice presentation. You wind the carbon fibers around the 3 trusses, you said, but they're only on top of the truss. And if you could able to wind it around this truss, would it help, or is the adhesion totally sufficient?
Yeah, that's a really good question. Yeah, so I think it would help. So but obviously you can't really do that easily without drastically changing or complicating the process. So one option is to stitch to stitch the joints afterwards. So sort of additional step. And that is something that we are looking at now. Yeah, but that is something he's looking at for sure.
Great, many great things to look at now. Thanks a lot, and thank you very much again for your talk.
Thank you.
Please now welcome Andreas Klinger from the Technical University of Kaiserslautern in Germany. Andreas has already some industrial experience working at Goodyear in Luxembourg. His PhD addresses fundamental understanding of how cracks propagates into composites. And the title of his talk today is From Brittle to Tough Damage Tolerance of Block Copolymer Toughened CFRPs. Andreas, are you ready?
Yes, I am.
Great. So 3, 2, 1, and go.
Hello, everybody. So imagine we live in a world where you can fly from New York City to Sydney in Australia within 20 hours without refueling. Imagine you can have wind energy turbines offshore, which are exposed to extreme wind loads, and you can supply energy to tens of thousands of households. All of this is already possible today to the excellent structures, to the excellent materials or properties of carbon fiber reinforced epoxies. We even take those materials and put them into cars. We create rims, for example. But the last example is also a very good example for demonstrating the challenges we are still facing with these materials. Imagine you're driving in the Swiss Alps with your nice BMW M4 GTS, and you're a little bit too fast. You accelerate too fast, and your car slides, and your rear hits the road boundary. Well, you will probably need to stop because the carbon fiber will be broken. So the inherent problem of carbon fiber reinforced epoxies is their brittleness. What can we do about it? Usually what is done, we can work on the layup. We can kind of restructure the layup to generate more energy dispersive mechanisms. But why not tackle the inherent property, the matrix itself? So one idea, or the origin itself, is that the high cross-link density is the problem for this brittleness. One idea would be to reduce the cross-link density for sure, but that will also affect a lot of other properties, and you will end up with a rubber. So the third approach is to put obstacles into the material, obstacles that can stop the crack, or the crack needs to interact with them, which dissipates energy in a certain way. You can either do that with rubber particles, but rubber particles will usually decrease your glass transition temperature, and that is a problem if your rim is closely located to the braking system. On the other hand, you can use stiff, rigid particles, for example, but they will need a lot of dispersion, energy-intensive dispersion efforts. So my approach is focusing on self-assembling macromolecules. What you do within what you do with these samples is you take those polymers, put them into your resin, and then during the curing process, these macromolecules phase separate into your obstacles, and then the crack can interact with them. So I focused on a bottom-up approach. I started first examining the phase separation process in our relatively complex resin system, which is usually containing a resin, a hardener, and an accelerator. We found out that we can, via the curing conditions, adapt the second phase morphology from a nanophase structure to a macrophase structure. However, forming the nanophase structures in our model system took about 2 weeks. It was quite difficult. So this is not a real approach for a manufacturing process. So we adapted our curing cycle, went on to the matrix level, and tested our fracture toughness for that. So what we found is already an enhancement of the interlaminar energy release rate of about 7-fold, meaning we were already able to drastically enhance our fracture toughness. In the next step, we transferred these macromolecules to the coupon level, where we had laminates included with carbon fibers. And what we found there, what was really interesting, due to the presence of the carbon fibers and the additional interfaces, we did not need anymore a really long curing cycle. The interfaces hindered the macrophase separation of these block copolymers, macromolecular structures, and we generated throughout the whole epoxy system nice nano-sized particulates. The nano-sized structure is therefore so relevant because it has a very high surface to volume ratio, right? And the more particles with a high surface you can put in there, the more is the likability that the crack can interact with those particles. So in the end, we were able, and that is one of the most exciting results, that we were able to drastically reduce the damage volume. As you can see on the lower left side of my slide, this is just a 2D representation, but the damage volume we were able to reduce the damage volume by about 67% in a thin laminate. Yeah, if we think about future applications, we will probably be able to drive through the Swiss Alps without any damage in our rim. Yeah, so thermodynamically driven self-assembling is, I think, what we need in future toughening applications for epoxy systems.
Thank you very much, Andreas, for this very inspiring talk. Do we have questions on the jury side? Yes, we have one.
Hello, and thank you for your presentation. Very interesting concept. I have one question. One question is regarding the viscosity of the resin. What is the impact of viscosity of resin if you add this kind of copolymer block polymers in the resin?
So if you go to this very high loading where we have this really strong reduction of the damage volume, you end up with a material you cannot really process in RTM or so on. So I think it's about 30 Pascal seconds if you talk about numbers. Yeah, but for sure, lower concentrations will enable easy processing. This was more or less a gradual increase, and we had already very good results getting lower concentrations in our material.
Okay, thank you. Okay.
Great. Thank you very much again. Thank you very much again for the questions. So we are at candidate number 8. Please welcome on stage Nicolas Lavalette from Delft University of Technology in the Netherlands. Nicolas is originally from France, but he graduated in the US and then worked in the car equipment in Paris. He moved back to academia to pursue a PhD looking at the design of new composite structures. The title of his talk today is Design and Optimization of Hybrid Truss Structures. Nicolas, are you ready?
I am. Thank you for the introduction.
Great. So 3, 2, 1, and go.
Good afternoon, everyone. Indeed, I'm going to present to you my work on the design and optimization of hybrid trusses. What is a truss, you may ask? A truss is a network of straight elements located precisely where needed to transfer loads. For example, I want you to picture the most famous truss in the world, the Eiffel Tower in Paris. Now imagine a virtual cylinder just large enough to contain it. The Eiffel Tower, which is made of iron, is lighter than the volume of air inside this cylinder. This illustrates how strong and relatively light trusses can be. Now, it's no secret that in many fields, like aerospace or robotics, light structures are preferable. My PhD is about developing trusses made of straight composite tubes. My goal is to optimize such a truss, to try to minimize its weight, for example. To achieve this, many optimization algorithms already exist. They can arrange the members to keep a good structural strength while minimizing the weight. However, they don't consider the weight of the joints that are used to connect the member together. The joints are added afterwards on the final solution, which can add a significant weight. I would like to consider the weight of the joints during the optimization to obtain overall lighter results. Naturally, the weight of each joint is related to how strong it needs to be. The stronger the joint, the heavier it is. So I need to know the relationship between the strength and the weight of the joints. So the 3 objectives of this PhD are first to design suitable joints for this application, then to be able to predict their strength and weights, and finally to implement them in the truss optimization algorithm. Let's first have a look at the joint design. I am dealing with composite members, so a good solution is to use adhesive bonding because you don't want to damage the composites. To maximize the bonding area, I designed the joint as an aluminum node with tubular extensions that overlap the members and adhesive in between the tubes. Having this overlap allows the adhesive to be spread over a larger surface, and this way there are only shear stresses within the adhesive, and it is where it is the strongest. To better understand the behavior of the joint, I manufactured several specimens, each representing a single truss member with a joint on both sides, and with different dimensions, length, diameter, etc., I tested them to obtain their failure loads in tension. In parallel, I made a finite element model to try to predict the failure loads, and after validating the model by comparing its prediction with the experiments, I could use it to optimize the dimensions of the joints. To obtain both the minimum weights and the maximum strength, I did a multi-objective optimization. What I obtained from this is not a single optimal solution, but rather several optimal combinations of strengths and weights. When you see them on the graph, these solutions appear to follow a trend. It means that I can approximate them with a numerical relationship that links the strength of the joint to its weight. So now, for each value of strength required for a joint, I know the optimal weight that this joint should have, and that is what I can use in the truss optimization. Now, during the truss optimization itself, the algorithm analyzes the structure and calculates the loads going through each member. Knowing that, it knows the strength required by each joint. And thanks to the numerical relationship obtained earlier, it knows how heavy each joint will be as a result. So by knowing the actual weight of each joint during the optimization, the algorithm will then optimize the truss to try to reduce these additional weights. It also acts as a feasibility constraint because we know the limit strength of the joints. And without it, a truss may be optimized but not feasible because, for example, nodes could be too close together and joints wouldn't be strong enough to carry the load. As a result, we obtain a final structure that is lighter and more realistic than if the joints were added after the optimization. Now, these results are obtained using one specific joint design, but maybe for different applications, different joint designs might be required. The point is that the joints are a critical aspect of a truss, especially when composites are involved. So by predicting their strength and involving them deeper in the design and the optimization processes, we can obtain better and lighter structures and eventually better and lighter aircraft, spacecrafts, and robots. Thank you for your attention.
Thank you very much, Nicolas, for this really nice talk on truss structures. Do we have a question from the jury? Yes, we have two. Let's start with Christian.
Okay, thanks a lot. It's also inspiring by nature that also in nature, a tree also is dimensionizing his trusses also, or his joints also due his forces. But also a tree never has got very straight, how do you call it in English? Umbra, how do you call it in English?
An arm.
Arm. If you imagine that you can also use bended trusses, do you think you can also reduce the material very much or not so much? Depends on the structure, of course. Do you also take this into account?
I did not take this into account because when you look at trusses, the basic assumption of trusses is that the elements are straight, and this is
because
the whole basis. Because that's true,
yes.
because it's man-made.
Yeah.
Yes. Maybe if we could be able to add curvature to it, we might obtain better results because we might avoid bending issues, for example. So it could be better indeed.
Yeah.
Great. Thanks a lot. Let's go for the second question.
Yes, thank you. Thank you, Nicolas, for your talk. A quick question on my side. You say that you need this extra components to connect the members. What do you think about using additive manufacturing to try to create the connectors? That will change something in your design?
That's a good question. Actually, the biggest unknown in this whole project is how to exactly manufacture and assemble the joints with the truss members. And it's not part of my project, but we had ideas, and additive manufacturing was indeed the preferred hypothetical solution to manufacture these joints, because then we could also optimize the joints themselves to make them hollow, for example, and save even more weight.
Thank you. Thank you. Thanks.
Great. Thank you very much, Nicola. Thank you again, and congratulations for your really nice talk. Let's move to the next candidate, Maria Morissalou from KU Leuven in Belgium. Originally from Philippines, she's pursuing her PhD on the European funding between Belgium and her original country. She's also assistant professor in the Philippines. She's working on flax composites, and the title of her talk today is Improving the Water Durability of Flax Fiber Composites by Using Non-Dry Fiber. Maria, are you ready?
Yes, I'm ready.
Really great. So 3, 2, 1, go.
So hello again. I'm Morissalou. I'm a PhD student here in KU Leuven, Belgium. So in the photos are the flax plant, the flax fiber extracted from the plant, and the flax composite that I'm working with. So compared to composites made of synthetic fibers, such as glass fiber, so flax composites have the advantage of lower environmental footprint, lower density, high specific strength and stiffness, and oftentimes at a moderate cost. But have you ever noticed that natural fiber composites in general are still unpopular in composite application? And what is the reason? So natural fibers such as flax is hydrophilic, which means that the material absorbs water. So the problem is flax fiber swells when it absorbs water and shrinks when it loses the water. So this swelling and shrinking of the fiber results in poor properties of the composites where they are used as reinforcement. So this issue of moisture absorption and fiber swelling in composites makes natural fiber an unpopular choice for large-scale composite application. So to lessen the effects of moisture on flax composites, our research aims to improve the moisture durability of the composite by using non-dry fiber and resin with low sensitivity to moisture for the production of composites. Because normally, oven-dried fibers are used to make composites. But when this composite is exposed to high moisture environment, it will definitely absorb water, resulting in cracks and damages, and eventually in the degradation of the properties of the whole composites. So compared to composites made of non-dry fiber, so since the fiber already contains some amount of moisture and is already partly swelled, then the effect of changing environmental condition on the composite is possibly less. So composites made of non-dry fiber could have less moisture absorbed, less microcracks, less damage in the interface, and also additional advantages of using non-dry fiber could be lesser cost and time saving in the manufacturing of composites, since the process of oven drying the fiber is eliminated. So this simple idea inspired us to investigate the potential benefit of using non-dry fiber over the oven-dried fiber in composites. So in this research, we hypothesized that for composites made of non-dry fiber, which already contains some amount of moisture and is already partly swelled, the swelling and shrinking of the composite due to moisture absorption is reduced, thereby retaining the dimensional and mechanical properties of the composites over time. So to test our hypothesis, in our study, we used accelerated aging for moisture durability evaluation, which is the wet-dry cycling. So we try to simulate both the hot-wet and then the hot-dry weather condition for both the indoor and outdoor applications of the composite. So the artificial aging that we use consists of 5 cycles divided into wet and then in the dry condition. And then in the wet condition, we use a relative humidity of around 89%. And then in the dry condition, we use a relative humidity of around 32%. And then we also tested the composites at different cycles to measure the progression of damage throughout the cycle. So after the durability study, the composites made of non-dry fiber have mean strength of around 18 to 20% higher than composites made of dried fiber. So indeed, the results show that composites made of non-dry fiber and resin with low sensitivity to moisture have lower degree of moisture absorption, lower degree of swelling and shrinking, and the mechanical property is better compared to composites made of dried fiber. Therefore, using this simple approach, not only did we enhance the moisture durability of the composite, we also lessen the time and cost of producing the composite by eliminating the pre-drying of the fibers. Thank you so much.
Thank you very much, Maria, for this talk and for this really interesting approach. Do we have questions from the jury? Yes, we do.
Yes, we have.
So now, Christophe, go ahead.
Thank you, Marisa, for your nice talk. I have a question. With this water which is absorbed by the flax fibers, what happened when you process a composite and then you expose these fibers to temperature higher than 100 degrees C to, let's say, to process a certain polymer? So what happened to this water?
Okay. We use epoxy, and then the post-curing temperature of epoxy is around 150. So what we did was we used pressure. So if you increase the pressure, you also increase the boiling temperature of water. So you will limit the boiling of the water. So we actually made a good composite using this epoxy.
Okay.
Yeah.
Thanks.
Thank you very much. Let's go for the second question.
Yeah, hello, and thank you for your interesting presentation and very engineer approach. It's very nice to consider this approach. I have one question for you is, do you consider or characterize the surface energy in the yarn? That means that look at the compatibility between the resin and the yarn if you use a dry fiber or if you use a non-dry fiber. And
I'm sorry again. Can you repeat the question, please?
Yeah, the question is, do you have a look on the compatibility between the resin and the dry fiber and the non-dry fiber? Is that the question?
The compatibility of the
on the surface, I would say, as you have the yarn.
Yes, of
you
course.
have water on one side and no water on the other side.
Yes, yes, yes.
When you make a composite, the interface is not the same, and you have more water on the surface, and that can as well have some effect on the compatibility. I don't know.
Okay, so thank you for the question. We actually compared our composite with composites made of dried fiber. So after the production, so we checked the addition of the fiber and then the resin. So our non-dry fiber and then the resin have almost the same property actually at the after production. So we don't have a problem with the addition. The same with the dried fiber and then resin.
Okay, thank you.
Okay.
Thank you very much all, and thank you very much, Maria, again for this really nice talk. We are already reaching candidate number 10. So now please welcome this candidate on stage, Amir Rahimi from McGill University in Canada. Originally from Iran, he graduated from McGill University, then pursuing his PhD over there. His research already got innovation awards, and he is working on the hot topic, composite waste management. The title of his talk today is Used Wind Turbines, a Recycling Solution. Amir, are you ready?
Yes, I am.
Really great. So 3, 2, 1, and go.
Hello. Global warming, food security, water scarcity. These are all one and the same fight that when we connect the dots between them, we get to one main culprit, which is climate change. A serious enemy of our Earth that has been mainly tackled through the significant growth of wind energy industry over the past couple of decades. Currently, over 340,000 of wind turbines are running all around the world, and they are contributing to approximately 5.3% of the total electrical generation, a number which has increased by over 10% since last year. Here in Canada, where I live, over 13,000 megawatt of wind energy is generated every year, and it is being used to power more than 3.4 million households. Although promising and environmentally friendly, this renewable generation of wind energy is associated with a major problem that has been swept under the carpet for many years. But now that problem is turning into a serious issue, steering the wind industry to come up with a solution. And the problem is the unsustainable disposal methods used for wind turbine blades. In fact, the glass fiber composites used in wind turbine blades feature a limited lifespan of 20 to 25 years. That being said, many wind turbines are not functional anymore, and many more are coming to the end of their life. Currently, landfill is the most commonly used unsustainable disposal method for wind turbine blades, a method which is associated with an ecological crisis, as leachates from wind turbine blades can infiltrate the underground water, endangering the life of many creatures living down there. Environmental legislations in many countries are now prohibiting the landfill of wind turbine blades, and they're asking for a more sustainable disposal method, or maybe recycling. I'm on a mission, and my responsibility is to design and validate a recycle methodology for wind turbine blades, a methodology which can be used to extract the valuable constituents from wind turbine blades and reuse them in another process that leads to a more valuable material. The recycling scheme that I have proposed starts with an efficient mechanical recycling, which is integrated with a classification operation to extract fibers featuring proper dimensional properties. Micromechanical analysis on over 400 single glass fibers extracted through this two-step process is the main driver of this recycling technique. Precisely measuring the mechanical properties of single fibers and their interfacial strength has helped us to obtain the most optimum parameters for this initial fiber extraction, so that fibers that provide maximum stiffening and strengthening are extracted from wind turbine waste. Following the classification operation, those single fibers are mixed with a proper thermoplastic resin, and they are put into an optimized double extrusion process that leads to recycled composite pellets, which can be then used in multiple composite manufacturing processes, such as compression molding or even 3D printing. A comprehensive set of analysis on 3D printed recycled parts has demonstrated the capability and potential of this recycling technique to produce stiff, strong, and thus value-added products out of wind turbine waste. Products which can be then added back to the same recycling system, creating a sustainable solution. Nevertheless, being fully recyclable in theory doesn't matter if the blades are not recycled in practice. Considering the critical need for fast development of renewable energy sources, now it's the time for wind turbine blades to end up in a recycling plant instead of landfill. So let's not have this be dismissed into the unconscious again. Instead, let's start a day, let's work together and address this critical issue. Thank you very much.
Thank you very much, Amir, for sharing with us your mission into the wind industry. I think we have a question from Veronique here.
Yes, thank you for this interesting presentation. I just have a question. What type of products do you plan to do with the recycled wind turbine blade? Certainly not wind turbine blades, I guess, because you have short fibers, but do you have any idea of specific products?
So yeah, there are some actually products, some prototypes that we have actually manufactured. But if I just want to give you one good example, is recently we collaborated with Stelia Aerospace here in Montreal, and we actually we had a contract with them, and we made a mold for them because the properties that we actually found for our recycled parts, of course, they can't be used in high-tech for high-tech products, but the mold that they wanted to use, the properties that they wanted, and match the properties that we were able to obtain from our recycled parts.
Okay, thank you.
Thank you very much.
Thanks a lot. We have a lot of questions here. We will be able to take only 3 from what I heard. Let's go to the next one. I propose Lucien. Let's go for your question.
Yeah, thank you. Thank you for your presentation. My question is, your process that you have been speaking on, is it extrapolable to other technology, over sectors of the industry? Because it's a general problem of recycling that we may have.
I'm sorry, I can't hear you properly.
I was saying that does your process of recycling will be applied to other material than windmill application?
Can your process be applied to other applications than wind?
Instead of wind turbine blades, not exactly. Just wind. Yeah, exactly. Yes, I think like the methodology that we try to develop is actually so the parameters that we. So I would say that the main technology that we are kind of like proud of is how we extract fibers and how we separate powder while keeping residual powder on single fibers, because we believe with our test that those residual powder remain on the surface of the fibers, contribute to what we actually need. They contribute to final properties. So the technique that we developed, we already tested on glass fiber composites from wind turbine blades, but now we're actually generalizing it on other composite parts. So for example, bathtubs, we're actually working on that. Bathtubs are made from glass fiber composites. Or even like we are going to work on carbon fiber composite waste as well.
Great, thanks a lot. If you keep the answer short, we will take the next one.
Yeah, sure, sorry.
So I propose, Christophe, you can go ahead, and then we take the one from Jean-Marc.
Yes, thank you. A quick question. What is the typical length of the fibers you recover from after the grinding?
So the critical length that we actually measure, of course, like it varies, but like the critical length that we measured, it's between, if I remember correctly, it's between 250 to 300 micrometers.
All right, thanks.
Yes, thank you very much.
Yeah.
Great, thanks a lot. Let's go for the last question.
Yes, and very quick question. Thank you for your presentation. Is do you consider, as you know, you are going to use energy to recycle your material? Do you use the LCR approach to quantify your environmental impact compared to the normal product we can use on the market? Do you use the LCR life cycle analysis method?
So that's actually life cycle assessment is what we're actually looking into right now. So this is what we're actually assessing right now, because what we know is that we are counting on environmental legislation. So we know that this is critical, this has to be done. And now the technique that we have developed, we're now looking into life cycle assessment of the products that we make, as well as life cycle assessment for the entire system.
Okay, thank you. Okay.
Thank you very much.
Great, thank you very much to everyone. And again, thank you to all the PhDs and the jury. Ladies and gentlemen, we are already reaching the end. Now the jury will deliberate to decide about the winner. The winner will be announced this afternoon at 2:30 p.m. CEST, together with the other awards from the programs of JEC, the Startup Booster, and the Innovation Awards. The next session will start at 2 p.m., just before the ceremony, with a great keynote presentation from Frankie Zapata, the French flying man. Thank you very much to all of you for attending this session. We hope you learned a lot from our 10 young researchers. And on behalf of JEC, I wish you the best for the rest of the show. Also, don't forget that more information on each research can be found in the Education Hub of JEC Connect Digital Trade Show. So don't hesitate to visit and come back for the awards this afternoon. So now, please, let's have a big round of virtual applause for all the PhDs finalists and our jury. And I would like to welcome all the jury, the presenters, and the PhDs on the screen for a screenshot to close this session. Great. Thank you very much to all and see you soon.